So I'm going to talk about propensity scoring, specifically for multiple treatments, which you don't see as often as you see for binary treatments. And I'm going to look at two applications, one to an EHR-derived study and one to a epidemiologic cohort. Okay. All right, so there we go. Outline, background, model formulation, simulation studies, application, conclusion. Okay, so this is motivated from large observational studies, which we know are increasingly available. For example, we have now access to electronic health records all over the place, registries in Europe. We have initiatives like the UK Biobank, which combine rich data, behavioral health, and even whole genome sequencing data, all linked to electronic health records. We have large epidemiologic databases like national surveys. So we have all these observational rich sources of information. We know that in these studies, treatments, exposures, alleles are not randomly assigned, which means people who receive a treatment may differ from those who do not, based on a set of confounders. Okay, so such covariate imbalance in observational studies makes causal inference challenging, right? And it's especially challenging for big data sets. If we're dealing with EHR data sets, we may have hundreds of clinical variables that could be confounders of a treatment outcome relationship. So in these cases, we often employ some causal inference technique. Propensity scoring is pretty popular. And for those who are new to propensity scoring, it's a method that aims to balance confounders between treatment groups, as would naturally occur in a randomized controlled trial. Right, in an RCT, in an ideal world, we assign treatments at random. In observational studies, treatments are assigned based on certain conditions that the patient may have. So we have imbalance of confounders across treatments. So propensity scoring theory is very well developed for binary treatments, and it's been used probably since the 60s or 70s when Donald Rubin first started the theoretical framework. But if you notice in the literature, methods for non-binary treatments, so ordinal treatments, categorical or disjoint treatments, and even continuous treatments that we commonly encounter in EHR data are relatively few. The focus has really been on binary propensity scoring. So this probably looks small to you, but this data, this is the UK Biobank data. So here's an example of all the rich information you get from that EHR database, right? It's enormous. We have it stored on our server. There's clinical imaging data, there's blood, urine, clinical, socio-demographic data, there's brain imaging data, there's self-reports about lifestyle risk factors, diets, family history of diseases. There's actually whole genome sequencing data, 2 million SNPs or more. There's wearable device data, and of course then we have prospective EHR-linked outcomes, which is nice, right, for determining incidence of disease. And there are thousands, tens of thousands of UK Biobank projects ongoing. Another example, and this is the one I actually analyzed because it was easier to gain access to. In the US, we have something called Cerner Health Facts EHR database that comprises 700 participating hospitals. So a large number of people there. We don't have the richness of data from UK Biobank, of course, but we have your typical demographics, physician encounters, diagnoses of the patient, procedures, labs, etc. Okay, so we queried this database to determine the association between vasopressor choice for the treatment of SAH, subarachnoid hemorrhage. Okay. So our goal was to determine in SAH patients which vasopressor of the 3 major vasopressors is most protective against mortality. Okay. of course, the query produced not only multiple vasopressor treatments, but they were given at varying doses. So if we think of binary propensity scoring, how do we go about estimating the causal effect of vasopressors on mortality when we have multiple treatments potentially given at multiple doses? So this research is derived from this actual question. Like, we really did not know how to resolve this. We did not know how to use propensity scoring to analyze this data set. Sorry, I don't know. Yeah. Okay, so multiple treatments propensity scoring is now where we are after having mined that database. So multiple treatments arise in all areas of modern comparative effectiveness research, not just in the study we designed. Mental health disorders, there are more than 13 pharmacological treatments for major depressive disorder, a similar number for PTSD, generalized anxiety disorder, obsessive compulsive disorder, substance use disorders. There's at least 4 treatments for alcoholism. Cancer, of course, we are often looking at continuous or ordinal doses and toxicities to see what is tolerated by patients. So we are often in this multiple treatments framework. So if you did a literature search, you will find some methods for multiple treatments propensity scoring, but what you don't find is a sort of principled framework that you find for the binary case, right? So there are many ad hoc extensions of the binary case for ordinal treatments or for multiple treatments. There aren't really many. There are maybe five methods that I would say are quite ad hoc extensions of those cases. And the reason is you don't obtain a scalar balancing score when you fit any kind of propensity model in the multiple treatment setting. That is one luxury of the binary propensity score setting that you do not have in the multiple treatment setting. So for the students in the class, I wanted to go through the notation and introduction of the binary setting before even going to the multiple treatment setting. Okay, so if we have n patients, I1 through n, TI is the treatment the patient I actually received. XI is their entire set of potential confounders. And YI is the observed outcome of interest. For us, that's mortality. We can make that binary. And then we have K, either continuous or disjoint treatments. Continuous in the ordinal case or the continuous case, disjoint in the multinomial case. Right, so 3 different vasopressors are 3 disjoint treatments. For binary propensity scoring, it's actually very simple, assuming your conditions for propensity scoring are met, which we won't get into. But in step 1, you fit a propensity model to estimate the probability of treatment, T given X, and that is your balancing score. So you simply fit a logistic regression in step 1, get your p hat, probability of treatment, given your confounders, and that's your balancing score to be used in a step 2 to adjust for bias in an outcome model for mortality, YI. And if that's all done correctly, you can obtain causal effects. Okay, so adjustment methods that we use in step 2 in a mortality model, for example, a logistic regression for mortality, you may stratify, you may match patients, or you may weight patients in that outcome model. All have their well-studied benefits and limitations in the binary setting. Okay, so step 1, fit a propensity model, such as logistic regression, get your p hat, and then stratify on that p hat, or match on that p hat, or weight on that p hat. That's step 2. Okay. So here I have it again, just with a little bit of notation, right? There's your p hat. You notice since it's just one, it's a scalar balancing score that encapsulates the confounding, right? Everything in X. And it's been proved many times over that this is a scalar balancing score. Thus, when I adjust for it in step 2, I get the causal estimates of interest. I'm just going to add an aside here that we used to just fit a logistic regression in step 1, but you could fit anything in step 1 that gives you a balancing score. You could fit a machine learning algorithm. Okay, and there's been a lot of publications on using some machine learning algorithm or non-parametric regression in step 1. It doesn't have to be logistic regression. It can be anything. These are the causal estimates of interest. You have to define which one you're first interested in. It's typically the ATE, or the average treatment effect. So all that is the difference in the expected value of Y. If subject I had received K prime versus K, right, it's counterfactual because only K is observable, so K prime is a different treatment. The difference in the expected values of those is the ATE. Slight difference here in average treatment effect in the treated. Here we condition on actually having received that treatment K. It's a slightly different causal estimate of interest. It's when not everyone in your population could receive every treatment. Okay, so it's conditional on having received the treatment you received. There's a lot of nuance between these two causal estimates. In general, for this talk, we focus on ATE, which is pretty easy to understand. All right, so what happens with multiple treatments propensity scoring? So now in step 1, we need a propensity model for K treatments. So any model that I fit, multinomial regression, ordinal regression, machine learning model, I'm going to get a generalized propensity score, which they call a GPS, which is a vector with each person's estimated probability of receiving each treatment, right? Treatment 1 through treatment K, where the last part of the vector is fully defined. Okay, so this is not a balancing score anymore, this is a vector. So now we leave the nice world of the balancing score literature where all the theory has been proved, and we have to figure out how to get causal effects, right? Okay, so as I said, this predicted vector can result from any modeling procedure you choose in step 1. Okay, I won't get into that. We all know how to produce a p-hat vector from, say, a multinomial regression model. So as I said, each resultant GPS element is the conditional probability, given confounders, of receiving treatment K. Okay, so an example vector, this person has a 30% probability of treatment 1, 10% probability of treatment 2, and a 60% probability of treatment 3 in my 3-treatment case. So I have information here, but it's not as simple information as that scalar p-hat. All right, so what has prior work done in the multiple treatment setting? Well, the most simple form of analysis was to conduct pairwise regressions, so you stay within the balancing score framework. Others have just used distance metrics and clustering tools to stratify or match GPS vectors. So I find the vector closest to this guy, and maybe I match them. Or maybe I just stratify vectors that all look similar to this. This is very hard in practice to do. But that is published and fairly well published. There's another method called within trio distance matching that only works for K equals 3. It's a way of matching for 3 treatments only. We want something more generalizable than this, that we may have 5 treatments. In general, the prior work are really if you read through the literature, it's ad hoc extensions of the binary setting, usually based on some multivariate distance. You don't get a scalar balancing score. The methods can also be limited in the number of treatments they allow. For example, one of the above methods only allowed 3 treatments. It's also limited in the type of adjustment they allow. Some methods work well with stratification. Other methods work well with inverse probability weighting. It's rare to find an approach that works well with all possible types of adjustment. Then there's some nuances here as well. I won't get into this one, but this one is important. Reproducible research has shown distance-based approaches are not appropriate for higher dimensional confounders. So if I have 9 variables on the right side of my model, I'm okay, but maybe I'll have 28 or 50 variables on the right side of my model. And that's where those distance-based approaches apparently break down. And this has been fairly well studied. Elizabeth Stewart is well known in propensity scoring. Okay, so this is just to summarize. They're computationally ad hoc. They're geared toward estimation of ATTs and not really ATEs. I didn't get into that, but that's the case. They're often applicable to certain outcome types. It's been shown they don't necessarily produce good balancing scores, and often don't apply when K is larger than 3. And I'll add, they're not really readily adaptable to the ordinal treatment setting either. So in sum, there is no scalar balancing score that captures the complex relation of counterfactuals to balance confounders across all K treatments or doses to easily produce ATEs. So we set out to find a scalar balancing score in the multiple treatments setting. Let's very quickly discuss the ordinal treatment setting. It's a special case of multiple treatments setting, and it's actually a little bit easier case. Okay, so in step 1, we literally found one single paper on ordinal propensity scoring. Fit a proportional odds regression model and estimate the linear predictor, x beta hat. Okay, this is a scalar. So you have a scalar balancing score from a proportional odds model in your step 1 for your ordinal treatment. And then in step 2, you could weight in your outcome model by the inverse probability of the treatment actually received, right? That will be the dose actually received since it's ordinal. Or you can match and stratify based on a distance metric. And this is a proposed distance metric, which is simply the difference between those 2 scalars for 2 different people. This is someone's xi beta hat, and this is someone else's xj beta hat, right? They're scalar resulting from the proportional odds model. So 2 linear predictors squared, that's a distance. And this is the doses received by those patients. So patient I got dose 1 and patient J got dose 4. That's going to make this small, which is going to make us more likely to match those patients, right? If this distance, this scalar, if this distance is small, then I want to match those people, right? So I and J will be matched for different, more easily matched when doses are different, as this denominator gets bigger, and this numerator just prevents a 0 here. Okay, so this is a nice distance metric. It's terrific to use if you can fit a proportional odds model. If you trust that model as your propensity model, then you just use this methodology from JASA. But what about when a strict parametric model is not correct in step 1? Okay, there's been lots of publications on using machine learning in step 1, not using parametric modeling in step 1. So now again, you don't get that simple parametric scalar balancing score like x beta hat. X beta hat comes from the proportional odds model. Okay, So we want a method that lends itself to the sort of big data causal analysis derived from EHR studies. It's not really big data, it's just we may have a lot of confounders, right? So we have multiple treatments, we have potentially complex covariate spaces, so many covariates, higher order terms, interactions. We want to be able to accommodate all of that. It's not going to happen in a proportional odds model, right? Okay, so we derive a scalar balancing score for the K treatment setting. The score does not depend on the chosen propensity model. So you may fit a parametric, non-parametric, or machine learning model, and you can still estimate this scalar balancing score very easily. And it's going to facilitate adaptation of the well-accepted adjustment methods from the binary setting, specifically matching and stratification. As an aside, it actually facilitates estimation of ATEs in addition to ATTs. Okay, so here's the approach. So we fit any propensity model and we get a generalized propensity score vector. Okay, then fit a CDF to each person's GPS vector using a one parameter function. The chosen one parameter function is a power function, and for dose D is given here, so that the CDF is simply modeled right here as the dose x to the exponent of A. Okay, this is a power function adapted from phase 1 dose finding trials. This has been used in other settings before. On the next slide, I'm going to adapt this to our case, which is a propensity score model. So adapted to the current setting, each person's CDF, conditional on their covariate vector, right, all their confounders, is now written like this. And then my function is a function of AI, I for individual. So I have one AI for each person's CDF. So I estimate each person's scalar balancing score AI, that's what I'm calling AI tilde, just by minimizing this distance here, which can be done using very old techniques, nonlinear least squares. So again, I get a GPS vector for each person. Well, I just sum across that vector to get their CDF, and then I model their CDF with a one parameter function. And that parameter is AI. Okay. I'm going to say that AI is a scalar balancing score. And I'm going to show you why this power function does well. We searched a lot of functions before relying on this one. So here are example CDFs produced by that power function for various A parameters. So I think A can realistically go from something like -7 to get a curve way up here, all the way to 7 to get a curve basically with all the weight at 1 over here. So here we've drawn -2 to 2. So I get these values of A, and I'm going to use those to stratify and match patients. Well, the next slide should show why that works. I'm going to go down 2 slides first. The power function happens to demonstrate excellent mapping for many different numbers of treatments, K, and we actually tested all the way up to K equals 10. We just simulate patient vectors, calculate the CDF, and map the CDF using the power function. So the dots here are the truth, and the curve is the actual mapping using the power function. So for 3 treatments, it's actually quite perfect. The curve goes through the patient's vector quite well. 4 treatments, still looking pretty good. And we calculated MSEs for all of these as well. And even up to 6 treatments, I'm still pretty closely mapping each patient's vector, right? The only time I can't map as well is when I have a very pathological vector, for example, 0, 0, 1. So a person has 100% probability of getting the third treatment. Those vectors don't map so great. At the same time, those kinds of vectors violate propensity scoring assumptions. So there's not a lot you can do when that's the scenario. When patients can't get treatment 1 or 2, you probably shouldn't even be in the propensity scoring framework. Okay, so just to go back on this slide, before we did that, we tried stuff for an entire year because other metrics seemed more obvious. So why not use Mahalanobis distance, KS test statistic? If we want to model the CDF, what about any other one parameter function? Well, none of those did well. Any other one parameter function that we found doesn't accurately model the patient's CDF. So that's why we relied on the older literature for the dose toxicity studies. So we think we have shown, at least by simulation, we get incredibly accurate modeling of this using the power function. So now all I have is what I'll call balancing score, though I have not yet proved it, an A tilde. So this is like my p hat from the binary logistic regression, right? So if AI and AJ are balancing scores for 2 subjects, ZI and ZJ are the doses they received, E is a tiny constant, then I can use this distance, right, to calculate a distance matrix and match patients based on the doses they actually received and their balancing score. This is the same distance metric taken from the JAZA paper 2001. It's no different. So I just calculate this distance or any other chosen distance, now based on my AI and AJ. So here's the proposed procedure, and we have a proposed procedure for the ordinal, multinomial, and continuous case. Continuous is a little bit different, and I don't spend time on that one. There's just no time. But the ordinal case is incredibly natural in this framework. So step 1, choose your potential confounders. That's always your step 1. Step 2, estimate your GPS vector from any propensity model you choose. Step 3, calculate the CDF of the vector. Fit the 1 parameter power function to each person's CDF. Get your A tilde for each subject. Based on this AI, AJ, calculate the distance matrix to determine the distance from each person to all others. Once you have the distance matrix, you can either match pairs or you can stratify patients. Of course, as always, part of propensity scoring procedure, you assess covariant balance after matching or stratifying. Oh, and step 8, conduct an appropriate outcome analysis, accounting for your matching and stratification. Okay, so a logistic regression with a random effect for pair is one example. Multinomial setting is not as obvious, right? Because there's no inherent ordering to my CDF has no meaning, right? I could change the treatments around and gotten a different CDF. But the procedure is actually the same. I follow the same steps, but I consider all the CDFs, K factorial CDFs in step 4, and choose the resultant A that produces the best covariant balance. So everything is the same above, except in step 4, I don't have 1 CDF like I do in the ordinal case because my doses are ordered. I have K factorial possible CDFs. So I permute them and find the one that minimizes the distance, or actually achieves the best covariate balance. And this may sound a little bit ad hoc, but it's actually not. So the approach is in line with some of what experts in the field do recommend in other settings. It's called the Covariant Balancing Propensity Score. A lot of these authors simply recommend search techniques to find the propensity score that best balances your confounders across treatment groups, because that's your goal. It doesn't matter if you do this repetitively, okay? Because the goal is balance. So we feel that this search, what maybe look a little bizarre in the beginning, is in line with this ideology, sort of philosophy. And then we have a very similar procedure for the continuous setting, but it involves a little resampling, but it fits quite naturally into the same framework because we still obtain an empirical CDF from a sampled PDF for each subject, and we still obtain a scalar parameter in the end, although the procedure is different, and I don't have time to get into it. So we have a procedure for ordinal. We're fairly solid that this is a nice procedure for ordered data because the CDF is one direction only. We have a procedure for multinomial treatments, and then we have a procedure for continuous treatments, all within the same framework. All right, so let's evaluate these via simulation. We use a very common simulation study design found in the literature. So we have varying confounder strengths for 9 simulated covariates. So some are very, well, one is strongly associated with treatment and outcome, and then you have moderately associated, and then you have some that are totally independent of treatment and outcome and are not confounders at all. Okay, so you have a range of everything, which mirrors real life, and this setup is often used. Okay, so we have all the way from strong confounders to not confounders at all that are going to enter our propensity score model. This is the other common setup. So remember, I have a propensity model here and an outcome model. It's a 2-step procedure. I can correctly or incorrectly specify both models. So it's common to look at all 4 of those scenarios with a strong focus on scenario 4, because in general, in real life, this is where you land, right? We probably don't have the right treatment model, and we probably don't have the right outcome model. So literature seems to focus on what's going on in scenario 4, because scenarios 1 through 3, usually you do pretty well. So we do a very basic simulation at first. This is a proportional odds model. So we're in the ordinal setting right now. Okay, I have K doses, capital K. K is 1, 2, or 3 for simplicity. This is just a linear model, right? All we've done is introduce a mismeasured covariate here. Okay, so this is an incorrect treatment model, right? So when I put the squared term here, I'm in the incorrect. If I don't have this squared term, I'm in my correct model. Here for the outcome, it's just mortality. So I have a logistic regression, again, with a mismeasured confounder, okay? So when I have this squared term, I'm in the incorrect scenario. And when I don't have this squared term, I'm in the correct scenario. All the others are modeled correctly. Now, importantly, this is our biggest confounder, right? This X1 was our strongest confounder. We want to see what happens. What is the breakdown like when we inappropriately model an important confounder? Okay, so I think all these details don't matter. We judiciously picked our betas. We went through lots of betas. There's nothing pathological here. This is a very standard setup. So how do we compare each method? We want to compare the method that we propose with existing methods, choosing the most commonly used existing method because we can't compare everything. Well, one is covariate balance produced. That's very important. You want to produce balance between matched pairs or within strata, right? That's the whole goal, is to balance confounders so that you can get causal effects. So you will check your covariate balance. And of course, you will also check your bias, your MSE, and your coverage probability for your causal estimate of interest, average treatment effect. Okay, both of these are important. In simulation, it's very hard to show this because imagine in 10,000 simulations, I'd have to average all the SMDs. So we pulled them out and looked at them. Here, I'm just presenting the bias in the ATE. So I'm presenting number 2, bias, MSE, and coverage probability. Yeah, a lot of info here. And that's because, remember, we had 4 scenarios. And we said in the literature, scenarios 1, 2, and 3 usually aren't problematic, and most methods work under those scenarios. Scenario 4 is the most problematic. So black bar shows the extent of bias. So the truth is the dotted line. So we want our black bar to go through the dotted line. On the x-axis are the different possible methods: unadjusted modeling, heavily biased, fitting a proportional odds model and matching, fitting a proportional odds model and stratifying, and then using the GPS CDF matching and stratification that we propose. Okay, so looking across the board here, similarly unbiased, because the models are correct. Both the treatment and outcome model are correct, so they better be unbiased. Similar coverage probabilities, not much going on here, small MSE. Over here, I have an incorrect treatment model, still doing okay. And same down here, incorrect outcome model, but correct treatment model, everything looking kind of similar. Now I'm going to focus on scenario 4. And this is the ordinal setting. Remember, that's why we're using the proportional odds model. So scenario 4 is where you see the breakdowns. You start to get large bias in your ATE because your treatment and your outcome model are incorrect. So for sure, the proportional odds model is wrong here because I violated proportional odds on purpose. Here, I'm not fitting a proportional odds model. I'm using GBM, generalized boosting. And therefore, I should do a little bit better than the proportional odds model. And then I'm matching based on a scalar from there. So, or stratifying based on a scalar from there. So in fact, we tend to see pretty good results for stratification. There is bias, but it's much smaller, 0.06. MSE is okay, and coverage probability is getting near the nominal level, especially versus the other methods that are the only other method that actually exists for ordinal data, which are these. You'd have to fit the proportional odds model. So we're happy we did a little better here. We're not surprised matching is not so good. Matching has issues. I can get into in a second. We do the same simulation for the multinomial treatment setting. The left side is no longer a proportional odds model. It's just a multinomial model, but the simulation setup is exactly the same. Okay, we had that one mismeasured confounder. Everything's okay in scenarios 1 through 3 so I'm not even going to focus on those. And I'm going to go to scenario 4. Now we have different comparisons here because there are different, for the multinomial setting, remember there's no principled framework. So now we're in a multinomial setting. We're going to use GBM with inverse probability treatment weighting because that's kind of, looks like the standard in the literature. And there's an easy R package called Twang that allows you to fit that. So we compare pretty much the gold standard right now for multinomial treatments in the literature, GBM with weighting, with our method using matching and stratification. So let's look at the biases. Okay, so this is a little more biased than ours. We get the 0.056 again. That's not a typo, it's the same bias actually. And 0.093 here. MSE, theirs is a little smaller, and coverage probability 0.89 versus 0.92. So potentially competitive, a little bit better with respect to bias. We do the same thing for the continuous setting, even though I didn't explain to you the continuous due to the lack of time. So I'm going to focus on scenario 4 again. This one's a little harder to see, so I blew it up. So again, we are actually comparing to pretty advanced methods in the causal inference field for propensity scoring. This is a covariate balancing generalized propensity score methodology. This is stratification, and these are our approaches. And I didn't go through them, I just told you they have a similar framework by balancing on that A, that scalar A. And we are doing a little bit better in terms of pretty much everything, bias, MSE similar, and coverage probabilities. Then this one, which is probably the most used method in the literature. This one is not, but could be. Okay, so we're able to decrease bias, and we're especially able to do that when stratifying versus matching. Okay, so in summary, I didn't show you everything because it's not possible, but propensity scoring, we learned first, is incredibly robust to propensity model misspecification. So there's a ton of literature saying your propensity model should be a machine learning model because machine learning accounts for higher order terms, automatically includes interactions, right? But we found using a parametric model was always fine in our case. You can actually do that in step 1. The CDF GPS approach that produces the scalar seems to do as well or better than other methods in scenarios 1 through 3. And in that scenario 4, where both propensity and outcome model are misspecified, it does seem to produce 1, pretty good covariate balance, and 2, less biased ATEs. Okay. So let's apply it to a large epidemiologic cohort that had an exposure that was ordinal. We have a local study at our school. It's a Mexican-American tobacco use in children study. Sought to determine whether exposure to smoking imagery in movies, SIM, influences cigarette experimentation. So does exposure to imagery cause teens to begin smoking? So exposure is continuous or ordinal. You could look at it either way. It's typically viewed as ordinal among the behaviorists that study this. Outcome is cigarette use or experimentation. Hypothesis is exposure to SIM causes a young person to experiment with cigarettes, if we adjust for these multiple sociodemographic and behavioral confounders. Okay, this table is large. All it's showing you is the multiple confounders that we had in this data set. And all of this is abbreviated, but they're behavioral confounders. They're about risk-taking behavior, drug and alcohol use, social disinhibition, etc. And demographics, of course. What we do notice is across the 4 exposure categories of SIM, we're getting very large, what are considered pretty large SMDs, standardized mean differences. This means that we have imbalance of these variables across our treatment groups. And where you see a star means a lot of imbalance. Okay, an SMD cutoff should be 0.2 max. Some people promote 0.10. So I've got at least 6 violators here, maybe more, six. So let's implement the CDF GPS matching procedure for the ordinal treatment or exposure. Here's another way of looking at my SMD. This is before matching. These are the same numbers you just saw on the previous slide for all those variables. So I have some very high SMDs, some strong imbalance in my data set, my confounders, that after matching, we just got very lucky and every single one went to 0.2 or less. And again, we like to use a cutoff of 0.1. It's actually getting more stringent nowadays, but we couldn't meet that cutoff. Okay, but we did meet the cutoff of 0.2. And our odds ratio was 1.53, excluding 1. So our conclusion was that exposure to smoking imagery does cause smoking experimentation in Mexican American teens. And that's probably not surprising. Okay, let's move to an EHR-derived study. So we said we would look at SAH, subarachnoid hemorrhage, a cerebrovascular condition with high mortality and complicated treatment regimen, we found out. 39,000 patients had a new diagnosis of SAH in our client hospitals. This many met inclusion criteria, clinical inclusion criteria. We discovered 3 vasopressors used for the treatment of SAH: dopamine, phenylephrine, and norepinephrine. So we performed a comparative effective analysis of the 3 and showed phenylephrine reduces mortality more than the other treatments. We published this and then decided to focus on the dose of phenylephrine. So we took phenylephrine patients only because the dosage differed quite dramatically. We could consider dose as an ordinal or a continuous treatment, right? We could bin it into clinically identifiable doses or just let it be. So we had 642 patients that got that, 270 pretreatment confounders, which we had to narrow down by GLM lasso because when we threw these into any machine learning model, it would not converge. So we actually had to narrow it down. And that's fine. We narrowed it down to 28 confounders. And our dose was a huge range. So we're certain there are some typos, that 37,000 milligrams is not a dose. But that's EHR data. And we spent many months cleaning it, and that's what we get. Let's just assume that's okay. And let's fit our propensity model using GBM, which is one of the gold standards out there, and then apply the CDF GPS method, both for the continuous treatment and for the ordinal treatment, because I can consider doses both ways. I was a little uncertain about the continuous because we clearly know this is wrong, right? If I make this an ordinal variable, I reduce its effect on my overall ATE. Okay, so here are the covariant balance plots when phenylephrine is considered as a continuous treatment. So here is our approach, stratification using the GPS CDF method. Here's GBM. I wouldn't propose GBM for a continuous variable. It probably doesn't make a lot of sense, but the authors do say you could use GPM with weighting for when you have a continuous variable, treatment variable. And this is from Annals of Applied Statistics. This is your covariant balancing generalized propensity score. Does okay in terms of getting an F statistic close to 0, meaning inducing balance in this data set for this continuous treatment. We're not using standardized mean differences here because we have a continuous treatment. We need to use something different, and this is generally what is used. It's an F statistic on T versus X linear regression model. So I blew this up. I got rid of this guy because it's hard to see and blew that rest of them up. So I think GPS CDF actually gives a little bit better balance than the covariate balancing GPS. That's just the way it fell for this particular data set. All right. And you can find those techniques in all of the references I have here. So let's focus first on the ordinal treatment ATEs. The ordinal balance looked quite similar to what we saw above. I didn't show it. And I want to look at ordinal because we had that crazy outlier and we don't really know if that's a correct treatment. Okay, so ATEs for the unadjusted show that phenylephrine has a negative effect on mortality, right? Higher mortality, the higher the dose, and it's actually significant. Well, that's probably because people who got that higher dose were more ill, right, to begin with. Adjustment didn't really help that OR, right? Just an adjusted regression model. When I apply GBM with inverse probability weighting, I attenuate that odds ratio a little bit, and it also becomes insignificant, which is what we believe clinically. Similarly, I'm going to go to GPS CDF stratification first, because it's attenuated even a little bit more and still insignificant. And then when I go to my most rigorous approach, which is matching, I match people based on a small caliper. Here, that's a more rigorous approach. I attenuate that OR even more and insignificant. So it's important to do sensitivity analyses like this when you are doing propensity scoring, because you just don't know if you should be even implementing propensity scoring because you can't test the assumptions of it. But if you see that you're unadjusted to adjusted to someone else's method, to your method, to a more stringent version of your method, begins to attenuate the ORs, you know, you might be going in the right direction, right? In fact, it's also almost starting to look protective, which is the clinical hypothesis. The continuous results are a little bit more awkward because all the ORs are 0.99, but the take-home message is that actually for our method, that 0.99 is still insignificant. However, it was also insignificant in the adjusted analysis too. That's because we probably had some typos in the data. Okay, so conclusions. Methods for multiple treatments propensity scoring are important given the increasing availability of large observational databases, registries, etc. Most methods are on the binary setting. Very few methods exist for multiple treatments. Some people promote always using machine learning propensity models, like I showed you, GBM with weighting. GBM does not support matching and stratification as adjustment methods, only inverse probability weighting. So our approach does, A, allow any propensity model for multiple outcomes, and B, allows adjustment via matching and stratification, sometimes preferable to IPW. Something important that we need to do is to prove A tilde is a balancing score in all three treatment settings, ordinal, multinomial, and continuous. We thought we did do that for the ordinal case, but reviewers thought otherwise. So we're working on that, and still some more analyses to do under a variety of simulation scenarios. All right. Merci de votre attention. Et il y a des questions?
Thank you, Satcia, very much for this very interesting talk. We have time for a few questions. So everybody is muted at the moment, but you can unmute and ask your question. For instance, Melanie, I see that you have some questions, so go ahead.
Yes, thank you very much for this very nice talk. So yes, I had two questions. So the first one is about matching on propensity score, because I remember, so I'm not very familiar to that, but I remember some work from Larry King at Harvard showing that it's not advisable to actually match on propensity score because it distorts the space. So I just wanted you to comment on that if possible. And the second question was when you explore scenario 4, where you have misspecification on both treatment and outcome model. I mean, you can have all type of misspecification, like it depends how misspecified you are. And just comment on if you explore different scheme of misspecification where you forget some covariate or you have the wrong parametric shape, or what did you explore?
Yeah. The answer to that is yes. I'll start with your first one about matching on the propensity score. I do completely agree that matching tends to produce more biased ATEs in my experience. I haven't read the paper you referred to from Harvard, but I will. One issue is you can't possibly match all patients within a very small caliper. So if you were to do optimal matching, there's different matching procedures, right? There's greedy, there's optimal. If you wanted to match your entire data set, you are distorting the space because you are getting patients who are not well matched, obviously, right? There are no matches for some people. So you're going to influence your ATE that way. I only would do matching if, say I had a registry with thousands of controls for every case. Well, then I might be able to find a very close control because I just have so many of them that my matching caliper would always be very, very tiny. So I might feel confident in that setting. But for the settings I've shown you here, I agree with you. We didn't even do matching. So when I have a huge control database, I would consider matching. Otherwise, I wouldn't. I think you're correct on that. Yes, regarding misspecification. So for our paper, we used a common misspecified regression for the most strong confounder, right? If your most strong confounder is misspecified, your model should break down and your ATE might break down, we would expect, right? But yeah, we explored, I mean, we generated data completely non-parametrically, right? According to no model whatsoever. We used different scenarios. We broke the proportional odds assumption in a more minor way. And our method was often competitive with the other methods throughout this. But it's weird that you can break the propensity model in quite a lot of ways and still do very, very well with your ATE. It can still be totally unbiased. And it's not something I understand. You can fit an absolutely wrong propensity model that does not match how you generated your data at all and still get an okay ATE. It's something we spent a lot of years on. So all those papers out there that say you have to use machine learning methods for your propensity scoring, I don't believe them. It looks like you don't. Logistic regression, cumulative logit model, multinomial regression seem to be usually, in any simulation I conducted, we're always fine, no matter how grossly misspecified that model was. I hope that answers.
Yes, Hélène, do you have a question as well?
Yes, thank you very much for your presentation. I would like also to come back on the question of robustness. Clearly, your method is much more robust than the other one, but my question is why is it so robust? And is it highly dependent on the method you used in the first step? Given the second step, your power function is a completely parametric model finally.
Right, no, you're right. The last step is not meaningful. I think it's because we're getting a scalar balancing score that represents the vector, and that does better than the distance matching type approaches that are out there. We don't do, I'm not gonna go say we do something way better, because if you let's just take a look here, you still see my screen, right? We all do well. in scenario 1, we all do well in scenario 2, we all do okay in scenario 3. If we're all going to do well, I like the method that has a scalar balancing score, right? And we all do fairly well in 4, but when I blow it up, we do a little bit better, right? It's not dramatically better. The bias here is 0.06, the bias there is 0.09. So we do a little better, but I like that it's a unified way of doing multiple treatments propensity scoring. So I think, to answer your question, it's based on the A hat, A tilde, appropriately mapping the CDF for every single patient pretty much all the time. Going back to that slide. I mean, this. I mean, any CDF shape can be fairly well matched by this power function. So if I'm modeling your CDF correctly, especially in the ordinal case, right? Well, whatever parameter is involved here, I should be able to match on that parameter or stratify on that parameter and get an ATE. That's what I think. But it's very hard to show this as a balancing score. Once that is shown, I think that this could be relevant, more relevant. Does that make sense, Elaine?
Yes, yes, thank you.
Okay, are there other questions?
Yes. Thank you for this nice talk. I just wanted to know if it's common to use a mixed model when you have cluster data or when you want to account for heterogeneity. It's just a random effect which can account for that in the propensity score, or do you have any other weighting methods?
So in the propensity score model you're asking, would you ever consider a random effect model?
Yeah. Is it common to account for the clustering?
Right, so now you're talking of a case where, so in step 2, yes, because you have clustering, right? Automatically in your second step, your adjustment, when you're looking at mortality, how treatment affects mortality, now your patients are correlated, so you do exactly what you say. In your propensity score model, I don't think it's typically needed unless, I guess you could have correlated patients. So yeah, I guess you could do it. You could do just a random effect model, get the best linear unbiased predictor, get a p-hat, and do the same type of matching or stratification that you would normally do.
Okay, thank you.
Okay.
Any other questions? Well, if not, we can thank Satcia once more. And the next seminar is Thursday, so very shortly. So at 1 p.m. French time. So thanks again, Satcia, and see you all soon.
See you next year. Bye.